So this week we're studying acceleration, but we can't really trust our finger to accelerate the cart down the track uniformly, so instead we've got this fan attached to the cart that is going to accelerate it for us. We're going to study 4 different types of motion, and I will show you all of them in this video. But before you begin, you first want to, as always, level your track. So you put your spirit level on here, double check that the bubble is exactly centered between the 2 lines, and if it's not, then there's a screw that the track rests on at this end of the track, and you can raise and lower this end of the track. So get it nice and level, and then you put the cart on the track, and what you're going to do is you would start the computer program, which I'm going to show you on screen in a moment, and then you turn on your cart and you'd let it accelerate. So like I said, we're going to study 4 different types of motion. The first one that you're going to be studying is we're going to start the cart from rest at 0, which in our case is actually the edge of the dead zone, so 15 centimeters. So you'll put it at 15 centimeters, but we're going to consider that to be 0. And you'll start the cart from rest and let the fan accelerate it down the track in the positive direction. So that looks like this. You would start your program running, and then you turn on the fan and release it from rest and let it accelerate down the track on its own. And that's the motion that you're going to take graphs of and talk about in your manual. So the manual does ask you a set of questions for each of the 4 types of motion we're studying. So now I'm going to take you over to the manual and talk about how you answer those questions for each of the 4 different cases. Now for all 4 of the motions that you're going to be studying in this experiment, there's 4 questions they're going to ask you. So in the first one they say, if the fan is moving in the way that's specified, describe how the position and velocity of the cart will change over time. So they're asking you to describe what the cart is going to do. So not the graphs, but the cart itself. In the second question, that's when they ask you to predict what you expect the graphs are going to look like for that motion. Now remember, in this experiment we've got constant acceleration due to that fan. So when there's constant acceleration, we expect the position time graph to be a curved line. And for constant acceleration, we expect the velocity time graph to be a straight line. So you'd get in here and draw whatever you think is appropriate for your predictions. You'd also want to, down here at the bottom, discuss a little bit about what you're predicting. The third question asks you to then do the experiment and capture the motion with your computer program. So that's where you're going to capture the graphs and then screen capture them and paste them into your report. Before you do that, however, you're going to want to fit a straight line to your velocity time graph. And I'm going to show you how to do that in the program in a moment. The fourth question then asks you to talk about the similarities and differences between your predicted graphs and the ones you actually measured using the equipment. And to get full marks for this, you do need to talk about both the similarities and the differences. So for the differences, you might talk about the bumps and wiggles and weirdness of the data. And for the similarities, it's never enough to say that the graphs look the same. You need to be very specific about how they were the same. So you might say, well, they were both linear with a positive slope or a negative slope or a 0 slope. And the y-intercept was 0 or it was larger than 0. So stuff like that. So now we'll demonstrate the program that we're going to be using this week. So as usual, you go find the 1100 folder, open that up, and last week we used the velocity program. This week we're going to use the acceleration program. So double-click to open that up. And the first thing you'll notice is that we have 2 graphs here. We have a position time graph and we have a velocity time graph. And I'm going to demonstrate this now, so bear with me, it'll be a little bit noisy. But what I'm going to do is I'm going to click the start button here. I'm going to turn on the fan and I'm going to release it from rest at the edge of the dead zone and let it accelerate down the track. So here's what this looks like. Click start, turn on the fan and let it accelerate. And as expected, the position time graph looks like a curved line and the velocity time graph looks like a straight line. So we want to fit a straight line to this velocity time graph, but before I do that, I first want to expand this a little just so I can see it better. So as demonstrated last week, if you want to resize things, first click on that graph to make sure it's the one selected, and then you would go to Display, Settings, go to the Axis Settings tab, and here under Extras, deselect Lock Origin Position and Lock Scaling. Click OK, and now I can hover my mouse over top of the line for the axes and I can drag the whole graph downward. I can also hover my mouse over top of the numbers and then click and drag to stretch that graph upwards. And as you can see, we've got a relatively linear section here, but there's a few bumps and wiggles. So to fit a straight line, you want to select data that looks pretty linear. So if you've got some wiggly bits, you're free to just avoid those. So you click and drag to highlight the area that actually looks linear. And then to fit a straight line to it, you're going to click on this button up here at the top that says Fit. And click the little arrow and choose Linear Fit. And it will put a straight line through the data. It also gives you this box of information. And by the way, you can click and drag the box around to put it in a more convenient location. If you decide you don't like the data that you chose, you can actually click and drag a new set of data. So in general, though, you want to just choose an area that looks fairly linear. And this is your slope value. You'll need to figure out what the units on this are. So as usual, you will screen capture these two graphs and paste them into your report. So now we're going to talk about the three next cases that you're going to study. So for all four of these cases, you're going to be answering those same questions in the manual. You'll describe the motion of the cart on the track, then you'll predict the graphs that you're going to see, then you'll actually capture those graphs and paste them into your report, and finally you'll talk about the similarities and differences between what you predicted that you would see for the graphs and what you actually did see. So in the first case, you were starting the cart from rest at the edge of the dead zone, R0, and letting it accelerate in the positive direction. The second motion that we're going to study, we want the cart to have an initial velocity. So how do we do that? Well, what we do is we move this guy right into the dead zone, and then when he gets to the 15 centimeters, he'll already have a velocity. So you would start your program, turn on the fan cart, release it, and it's already got a velocity when it gets to here. So the third case is a little more tricky, because what we're going to do is we're going to take the cart, we're going to move it down here to the far end of the track, and we're going to actually turn on the fan and give the cart a push towards the sensor. So back in this direction, and what'll happen is that the fan is going to slow down the cart, stop it, and then start accelerating it back towards the other end of the track, so back in the positive direction. So that looks like this. You would start your program running, turn on the fan cart, and then give it a push towards the sensor. It'll slow itself down, stop, and start accelerating back in the positive direction again. And that's the motion that you want to get a graph of. Now I just want to show you a bit of weirdness in the data that you may or may not see on this third case. So, spoiler alert, this is roughly what your graphs are going to look like for this third case where the cart turned itself around. The weird thing you might see is that the velocity time graph isn't quite linear. So what I mean is, if I highlight these data here and put a linear fit on them, you get a nice straight line, but it doesn't match the slope up here. And likewise, if I highlight this data instead, it looks nice and linear, but it doesn't match the slope down here. So we've got two separate sections that are linear, rather than just one. Now the fan that we're using is supposed to give us constant acceleration, right? It's not getting stronger or weaker in the middle of the experiment. So if you see this, there's something else causing it. It's not the fan. There's some other reason why we're getting two different accelerations when we're not supposed to. And again, this is something you're not supposed to see theoretically, but it is pretty common with our equipment that you would see this bend in the data. So if you do, you and your group should talk about why you think that might be happening, because there is a question later in the manual that asks you about whether you saw this. So just to give you a little bit of hint about why it might be happening, note that this bend in the data is happening right when the velocity is 0. So right at 0, where this horizontal line is. So the velocity was equal to 0 when the cart changed direction, right? It slowed down, stopped for just a split second, and started moving in the other direction. So the change in acceleration happened when the cart changed direction. What could have caused that? Discuss it with your partners and try and figure it out. And again, your group may not see this, but if you do, highlight just one half of your data, like I've done, and then later on you'll be asked to discuss why you think this change in the acceleration happened. And for our fourth motion, what we're going to do is we're going to take the fan, turn it around, and we're actually going to start it at the far end of the track and let it accelerate towards the sensor. Please catch it before it crashes into your sensor, but that's the motion that you're going to capture. You turn on the fan, and it's going to push it towards the sensor, like this. And then just make sure you capture it before it crashes into your sensor. Now questions 5 and beyond are a little tricky, so I'm going to give you a few hints here. Not the answers, but just some hints on how to do these. So in question 5, they say, describe a real-world situation where the acceleration is in the same direction as the direction of motion, or the acceleration is in the opposite direction as the direction of motion. So you might want to think about things like a cart accelerating or decelerating, or a ball being thrown up in the air, stuff like that. In question 6, they say, using the apparatus provided, suggest how we could produce an acceleration that was larger than the ones we measured, or an acceleration smaller than the ones measured. So what they're asking you to do is to think about ways that you could tweak the track, or the cart itself, or the fan itself, in order to change the acceleration that we measured. So there's more than one way to do this, and more than one right answer. In question 7, they're saying, describe a real-world situation where an object has a large acceleration but a small velocity, and a small acceleration but a large velocity. So again, think about real-world cases where this is true. So in the first one, a large acceleration but a small velocity, basically what you're trying to think up is a case where something is not moving fast yet, but it's going to because it has a large acceleration. So small velocity right now, but a large acceleration, which means it's going to have a different velocity very soon. And for the second one, a small acceleration but a large velocity, think about something that's moving fast right now, but its velocity isn't going to change much because the acceleration is not very large. In question 8, they say, using your data and fit lines, find a value for the acceleration of all 4 cases that we've studied. Now, by the time you get to this question, you've already got those numbers. You don't need to do any calculations here. You should be able to just go and look up the numbers and write them down here. Questions 9 and 10 are actually related to each other. So question 9 is, why were the first 3 measured accelerations that we studied all positive accelerations? And question 10 says, which acceleration magnitudes roughly agree with each other? And then discuss why they might have. So these are a little tricky, but one thing that helps you answer these 2 questions is to remember that we only had one fan. All the accelerations we measured came from the same device. So if you keep that in mind, it helps you answer these 2 questions. And finally, down here at the bottom, did you notice any differences in the acceleration magnitude related to the direction of motion? So as I hinted before, this has to do with that third case where the cart changed direction. Did you see that bend in the data when the cart turned around? If you did, you want to explain why that might have happened.